Okay, welcome back, guys. We continue with our 9th lecture of our course, Math405, Learning from Data. And I'll do a quick review here. If you have any question, of course, you're welcome. I will do a quick review of what was covered during the last 2 lectures. And I'll go ahead with 1.8. which is about singular values and singular vectors in the SVD. Okay. So what we covered last time, we talked about symmetric matrices and how they have real eigenvalues. We talked about what is a positive definite matrices, and we solved 2 minimization problems based on the positiveness of the matrices. Okay. So mainly, we said that that all n eigenvalues of symmetric matrix S are real numbers, and that the eigenvectors that could be generated can be chosen to be orthogonal, and the eigenvector matrix, which we can call Q, has some properties that its transpose is equal to its inverse. So for every real symmetric matrix, you can easily apply the spectral theorem, which we talked about early in this course. The question was asked, what about complex matrices? Well, this property extends somehow to complex matrices when S equals the transpose of its conjugate. And we all know what is a conjugate of complex numbers, so we can, by extension, work on the conjugate of a complex matrix. And we've shown that this kind of matrices, they do have real eigenvalues, not the same case for their eigenvectors. And somehow we can also verify the orthogonality of the eigenvectors generated using the complex extension of the orthogonality. We've worked out a case on some matrices like this one S, which verifies the symmetry, and we found the eigenvalues, and we said that it could be used to generate other matrices which do have the same eigenvalues too. Then we proceeded with the kind of tests we have for positiveness of matrices. Well, the first one was called the energy test. Basically, it consisted on verifying that you have xt times sx, which needs to be either strictly positive or positive equal to 0. In that case, you call it positive semi-definite. And we've seen how we can complete the square for this formula, so we can show that it's also always positive. But in the second case, for the second matrix 5, 6, 6, 7, we said that was not possible, so we needed to work our case on some other tests. One of the tests was to write ATA using S equals ATA using A with independent columns. And we've seen the leading determinant test. So how to do that? How to write ATA as equal to S. So why these columns of A needs to be independent? Because if they're not independent, well, the null space is 0, and basically the energy test fails. So the energy is length the square of the vector. If the length square of the vector, and this energy is equal to 0 if this energy is positive. I'm sorry. Provided that AX is not the 0 vector. So to ensure that AX is not equal to 0 when X is different from 0, one might say that A must have independent columns. So for example, here we see that AT and A, they have independent columns. They have dependent columns. So this matrix cannot be said to be positive definite. Okay, so the leading determinant test, we've seen what we said that this is maybe the quickest method for, or the quickest test for small matrices. And these are the leading determinants of these kind of matrices. Of course, we're still talking about square matrices here. And there was a relation between these determinants and the kind of peoples when we do the LU elimination. And we said that every time you do the LU elimination, you're going to get dk over dk minus 1, which is equal to the kth peoples. Okay, so for example, in working on case on this matrix, which is basically symmetric, by the way, we found L, we found U. Okay, and we said that we can pull out the pivots and put them on a single matrix we called D. Okay, and write down here LT and L and LT. Sorry. Okay, and we did a little bit more. We said that if we can define the two matrices just as they do contain the square roots of the components we've seen early on, okay, in LT and L, one can say that we do obtain the two matrices ATA, okay, and this is what we call the Scholastic Factorization, okay, with the roots of the pivots on the main diagonal. So to apply this factorization, we need the S to be positive definite, and one must find at least one possible A. And of course, there could be many choices for A, including symmetric triangle. So it's very easy in the case of the symmetric case because you get a spectral factorization, and one can easily extend this. Basically, this is what we talked about last time, and finally we came out with a final definition of a final application of to positive definite matrices. We said that in the case of the minimization problem, and of course by reciprocity in the case of maximization problem, if we are looking for the minimum of a two-variable function here, we have to verify what we call in general here. We call them the first order condition for those in system engineering, where they know a lot about this in operations research or linear and nonlinear programming. So this is the first order condition, as you know. And for the positive definite matrix, which is usually called the Asian matrix, we need to make sure that it's positive definite to certify that we do have a minimum. Okay? And the graph goes upward when the second derivative matrix is positive definite. Okay? So we've seen these two examples, like for example, 5x squared plus 5y squared. We do obtain one single stationary point, or critical point, and at that point, the Asian matrix is positive definite, and this is where the minimum should be. And for the second case, we do have also 0, 0 as a solution. It's not the case all the time, of course, and the Asian matrix is also positive. Okay. So I'll proceed now, starting from the material for 1.8, and this is one of the, as we said early on, that single vector decomposition is one of the most important topics when it comes to talking about learning from data, and we will explain why. So in the couple of few slides, I'll give the main ideas behind this. So when it comes to treating and dealing with huge data, we would say that the base matrices are real symmetric matrices, but it's not the case all the time. Why they are best? Because they have real eigenvalues, as we've seen, and they have orthogonal eigenvectors. But it's not the case all the time. So for other matrices, the eigenvalues could be complex, and the eigenvectors could maybe not be always orthogonal. So if A is not square, when we try to solve this equation, AX equals lambda X, of course you know that it's impossible, basically, because you cannot talk about finding a determinant. Okay? And we need to work on an idea that succeeds for every matrix, if you get my point. So this idea is, in fact, what comes to be the singular value decomposition, which fills this gap, in fact, in a perfect way, because it extends the idea of finding this kind of factorization even to non-square matrices, which is very beautiful. So for example, let's talk about some application. Let's suppose in our application that we have a matrix of data, and the rows could tell us, for example, about the age and the height of 1,000 children. Okay, so for statistical representativity, if you wish. So basically, you have how many entries? You have 2 rows, one for the height, one for the age, and you have 1,000 columns. Okay, so the matrix is definitely rectangular; it cannot be said to be square or neither symmetric. So unless height is exactly proportional to age, the rank of that matrix would be 2. Okay. So that matrix has 2 positive singular values. We said that in our case, we'll look for these singular values, what we call the singular values. Okay? And the key point is that we need 2 sets of singular vectors, U's and V's, that are orthogonal to complete our factorization. Okay? And this is the main idea. The main idea is to be able to find 2 sets of vectors, V's and U's, such that for every pair of vectors V1 R and VU1, or in general for VR and UR, you can write AVR equal sigma R UR. So this is the main idea. The main idea is to be able to write AVK, for instance, equals sigma K UK. Okay? Now, this goes for a subscript or an index going from 1 to R, which is the rank of the matrix. Okay. Above R, everything should be equal to 0, because basically we're able to determine that these lines or these columns or these rows are redundant. So AVR plus 1 equals 0 till AVN, for instance. So for a real n by n matrix, A is n by n, which means it contains n rows and n columns. The n, لو سمحتوا شباب خلونا نتحكم في السكرين. So the n right singular vectors, v1 and vn, are integral in Rn. So basically, we're able to generate a basis in Rn. And the m left singular vectors un to um are perpendicular to each other in Rn. Okay? So we were able to define a basis, orthogonal basis in Rn. And what happens that when you multiply A by V, it gives you sigma U. So we will have R positive singular values we define to be called sigma 1 to sigma R. And the last n minus R V's are in the node space of A, which means AV R plus 1 till AVN is equal to 0. While the last m minus Ru's also are in the left node space. Okay? Right. Now the question, how to formulate that? Okay, beautiful idea. So the idea is to come up with something that looks, remember Shabab, the idea of bringing the eigenvector was to say that A lambda AX equals lambda X. So this is how we determine the eigenvectors. Am I right? Okay, and we said that this doesn't work for non-square matrix, basically because you're not able to find the lambdas. Okay, so we try to come up with something that looks quite close. Okay, which is this formulation: AV equals U sigma. This is the formulation. It is quite close to the formulation using the lambdas and the x's, or the eigenvalues and the eigenvectors. And in a detailed form, it means that A, in fact, could be written as the vector of U's, the vectors you were able to generate in Rm, multiplied by the sigma matrix, which contains it's a diagonal matrix, which contains all the sigmas in this diagonal. Everything above is 0, below is 0. and everything beyond R is 0, whether in column or in rows. Okay, and finally you can put all the V vectors from V1 till Vn. Of course, you can stop at Vr. Those are the most interesting ones. The other ones are in the null space. Okay, those from R plus 1 to Vn, as we said in the definition, are in the null space. Similarly here, from UR plus 1 to UN, we are in the left null space, or the null space of AT. And the idea is to come up with this kind of factorization, which is the U sigma V factorization. And these values, in fact, the sigmas, are the what we call the single values, while the U's and the V's are the single vectors, or singular vectors. Hello? So the idea, if someone just joins and he wants to know what is the main point here, the main point is that we can try to extend the notion of eigenvalues and eigenvectors to non-square matrices and do the same kind of factorization we did before. While the notion of the determinant doesn't extend to non-square matrices, we will be able to work our ways and define what we call singular values, which kind of are something similar to eigenvalues, and singular vectors, which are quite close to eigenvectors. And these vectors, they somehow verify the properties verified by the eigenvectors. Similarly for the singular values. Okay, and the main idea is to get this kind of factorization now, where A is equal to U sigma Vt. And now the question that needs to be asked is how to find these values. Okay, and there are some mathematical tricks which are, well, very, very beautiful. We'll see, and we'll see how to get to this point. Okay. The question again: why do we have to do this while we are talking about learning from data and exploring data? Well, as we said in the small application description, not all the data we can obtain are providing square matrices. Okay. Moreover, you could be more interested in approximating these matrices, as we will see later on. Okay. Any questions, guys? Can I proceed? Okay, so go ahead if you have any question. You can interrupt me anymore. So, for example, if I take this matrix here, A, this is A to me, 3, 0, 4, 5. And I'm saying that this is V. This guy, 1 divided by square root of 2, 1 minus 1, 1, 1, is equal to 1 over root of 10 times 1 minus 3 over 3, and 3, 1. And the last part is supposed to be the sigma, okay? This is just, I mean, I'm throwing this just to attract your attention that, well, this works, okay? Even though you can see that A here is not, we could observe that A is not symmetric, okay? Like, if A is not symmetric, it means that we don't have this characteristic that it has positive real eigenvalues. Okay. Moreover, you could observe that if these are the vectors in V, so V1 and V2, you can see that they are orthogonal. In fact, their dot product gives a 0. Similarly here, if this is U, the dot product gives a 0. Okay. You can see that we have minus 3 plus 3 gives a 0. And well, interesting. You can see also the entries in the diagonal of sigma are positive. Okay. So for this matrix, we will show later on that these singular values, these are the singular values we could obtain, and their product happens to be to verify the same characteristic we've seen for eigenvalues, is that their product is equal to the determinant. Their product here, 3 by 5, as you see, if you do the multiplication, is equal to the determinant of A, as you see. So somehow it looks like the eigenvalues are here, but they have different name. So their product 3 times 5 equals 15. is a determinant of A. In this respect, single values, I quite like the eigenvalues. You observe that the columns of V are orthogonal, and the columns of U are also orthogonal. And they have unit vectors, unit lengths, because of the division here by 1 over root of 2, because the length of the first vector is root of 2, and the length of the second vector is also root of 2. Similarly, for the vectors in U, U1 and U2, the norms are root of 10 and root of 10. Okay, guys? Could you give me just a second, please? Okay, guys. Sorry for the interruption. So those columns, yes, I can. Any question, Rakan? So those columns are unit vectors that after division by root of 2 and root of 10. But the question is that we did not explain how we got these. So this is, and the remaining of the talk, we will detail how one can obtain from scratch, from any given matrix, these singular values and singular values. Okay? Any question, guys? Okay, so let me proceed. So what needs first to be understood is important. Before you work your way on finding a solution to a problem, you need to deeply understand what is beyond. Okay, why is it so important for the subject? And this book, or this in fact this talk. So like other factorization, we've seen. First one we've seen is the LU elimination or the QR elimination, which was very simple. The spectral factorization, what it does, it writes the matrix into rank 1 pieces. Okay, if we are able to rank a whole huge data into the sum of rank 1 matrices, well, it's beautiful. You'll be able to decompose your data, to understand it deeply, and moreover, to store it in an appropriate way, compress it if you wish. Okay? So a special property of the SVD is that those pieces come in order of importance. What do you mean? They will be aligned in order in a way that they go from the largest one to the smallest one. Okay? So the first piece, for example, sigma 1 u1 v1 t, which is a rank 1 matrix, by the way, would be the closest rank 1 matrix to A. Okay? And more than that is true. The sum of the first k pieces is the best possible for rank k. Okay? So in general, one could say that we have something of this kind, that AK which is kind of the best possible for a rank k matrix, is better approximated by this kind of formulation, which is the sum of these products, sigma 1 u1 v1 t till sigma k u k v vk, is the best rank k approximation to A. Okay. Now let me ask a question. I hope everyone will be very careful. And I won't give you any answer. Can you think about something you've already seen at a few p.m. in one of the mathematics course that reminds you of this? Go ahead. Can you think about something you've seen in one of the math courses that reminds you of this? That once you do this, you have the best rank or the best kind of approximation to an original function or an original information. You can dig a little bit left and right. You can just remember the courses, the mathematics courses. I'm pretty sure everyone took it. It's a core course. Aziz, Firas, are you here?
Yes.
Yes, we are here.
So what do you think? Do you remember something that looks, that shares maybe the same property, some analogy with what is said here? Anyone else? Rakan, Khalid.
Is it just as a series with the approximation like?
Khalid, yes, go ahead. Taylor Mclaren series.
Is it,
what do they do?
Yes. Because it's an approximation.
They try to approximate. Yeah, this is an approximation of a function. So exactly, this is wonderful, Khalid. So Taylor Mclaren series, they do provide a general formulation for a polynomial approximation of any differentiable function. So, and if you get back to the 102 course, we usually stop at some order, right? The nth order. Okay, so basically we're extracting the best information we could get from the n first derivatives. And we say that if we take the n first derivative, this polynomial gives you the best approximation to your function at this point. Am I right? So somehow here, it's telling us that if you take the k first singular vectors, they give you the best rank k approximation to A. Got it? So you understand that when you add more information, yes, you gain accuracy, but you're wasting time. Okay? So basically, we're trying to compress the information to get the core information, the most important part of the information, the first singular values and singular vectors we generate. Okay? Thank you very much, Khalid. This is the fundamental point we're trying to do here. Okay? We're trying to approximate a set of huge data using small matrices. So there is a fundamental theorem, in fact, in linear algebra by Eckhart and Young that says that for any other matrix P which has a rank k, you will always have the distance from A to AK, which is less or equal to the distance from A. Okay? You'll always have this. So AK is the best rank k approximation of A. Right. Now, how to do it? The whole question and the core and the most fundamental part in this talk is how to be able to do this. So let's start by some fundamental observation. So one can first see that if assuming that U is equal to sigma VT, sigma here in capital, of course, big letter, well, you can work your ways in two different directions. First of all, let us write AT times A, okay? So here, I should probably remove this. This is a typo, guys. So AT times A, well, you know that by extension of the transposition here, if I write U sigma VT all transpose, one of the fundamental properties when you do transposition in linear algebra, that this gives you, in fact, it inverts the order. So it gives you V sigma T when the T goes inside UT. Am I right? Okay. So this part is, you see here in the first bracket, is AT. When I do AT by A, this is A, what happens between here, when you open the brackets, is that UTU, as you said in your definition, as we said in our definition, we need the U's to be orthogonal. So the UTU is an identity matrix, in fact. Got it? So UTU is an identity matrix, which means that you come up with something like this, that basically you're saying that ATA needs to be equal to V times sigma T times sigma times VT, first of all. But this is the first result, let's call it 1. Secondly, if you do the other direction, if you place A first and you multiply by AT, you're gonna have the kind of getting the same thing, but now with VT times V. This is equals to I also. Why? Because the V's are supposed to be orthogonal to each other, which means you end up with this matrix: U times sigma T times UT. Okay? So in general, ATA and AAT are generally different, of course. But both sides have the same form as the spectral factorization. And it's wonderful if you can get a spectral factorization for ATA. And this is the main point. So what about computing now the lambdas, I mean the eigenvalues of these two matrices, sigma T sigma and sigma T. And considering that, well, the V's would be the eigenvectors of Q or of Q on the other side. So whether you consider that Q is equal to V and the first multiplication, TA, so basically Q plays the role of V here, and the second one you will say that Q is equal to U. Okay? So in definition we said that the SVDs are obtained with V as orthonormal vectors, orthonormal eigenvectors of what? Of ATA. So let's do a separation. And the U's are the orthonormal eigenvectors of AAT. Okay? So if you use the first equation and you use the V's to determine the eigenvectors of ATA, and you can use the U's as the orthonormal eigenvectors of AAT, well, the sigma 1 square and sigma till sigma r squares are the zero eigenvalues of both matrices ATA and AAT. And this is the way we'll be doing it. Okay? You get it, guys? Any question? So the main idea to, yes, Abdulaziz?
Doctor, the multiplication sigma by sigma transpose, should it give the identity matrix?
No, the sigma is an identity matrix, which is a diagonal, the sigma is a diagonal matrix where the diagonal is composed, it has these singular values. You get it?
Yes.
Okay, so like in the previous slide here, I gave you, we gave an example. So this is the, in fact, the sigma, you see it? Okay. So when you multiply the sigma, for example, by its transpose, you don't get the identity. This is one case, just to say, okay? And it's not to be that case. Now, the most important thing is that to understand that the U's are orthogonal to each other and the V's are orthogonal to each other because they do form, respectively, orthogonal basis in Rn and Rn. And that's why when you do the multiplication UT by U in the first case and VT by V in the second case, you get I, which makes the formulation much easier to understand. And then you can consider that here in the first case, Q plays the role of V, and the second case, Q plays the role of U, so you can extract the eigenvectors. Okay? So let's set one example, okay, guys? Are you okay with this? So this is a matrix, the same matrix A, and we kind of try to show here how we got this, how we got these matrices. So if one writes the matrix 3045, okay, well, it's not symmetric, which might be mind-boggling here. However, we obtain the two matrices ATA and AAT, which are fundamental in the next part of the job, okay? Of course, you can see that they are different, which is generally the case. By the way, you could notice, Shabab, that even A is not square here, ATA or AAT will always end up to be squared. Am I right? Okay. Even if A is not squared, so suppose it's n by m. If you do ATA, this is going to be end up to be an m by m, and AAT is going to be n by n. Am I right? So in all cases, these two matrices, which are different, and you see in terms of size, they theoretically have different sizes if you assume that the matrix is not squared. So you end up with two beautiful square matrices, at least. Okay? So they both have the same trace, as you can see. Sorry, they have the trace and the same eigenvalues. Sorry, what was I saying? So they have the trace and the same values, as you see. So the point is, first of all, let's try to find the eigenvalues. And the eigenvalues of these two matrices, we can easily find them because we need to solve just the determinant of this matrix ATA or AAT minus lambda I equals 0. So here in this case, you can work your ways and you get the two eigenvectors, which are positive. And these are called sigma 1 squared here, sigma 2 squared. Why? Well, in fact, we'll go till K, till R. What is R here? The rank is 2, as you see for our matrix A. It's very easy. So once you got these eigenvalues, 45 and 5, you can get the eigenvectors. Yes, Nawaf?
Doctor, are the eigenvalues of ATA and AA transpose will be always the same, or it's different?
Well, we said, Nawaf, thank you for the very beautiful question. Well, theoretically, Nawaf, we said that they are not the same, they do not have the same size. Okay? So this is typical to this case only, because these two matrices have the same size.
Okay.
And numerically speaking, I'm not sure we will have if the two matrices ATA and AAT are the same size, we always have the same eigenvalues. Okay? So, but in general, it's not the case at all, because one would have, for example, n eigenvalues, the other one would have m eigenvalues, as you understand. Got my point? Okay. So once you got these eigenvalues, we can extract the eigenvectors, of course. We can use them to extract the eigenvectors. For example, I can use the 45 to generate the two respective eigenvectors, 1, 1, and 1 minus 1 for AAT, the first one. And you can observe that they are orthogonal, but they are not orthonormal yet. What do we mean by orthonormal? They don't have a unit norm. That's why we need to divide by their norm, okay, or their length. You got it, guys? Right. So this is half of the job done. So the right values or the V's were obtained now. So these are the components in V now. Found them. Similarly, we found the singular values. Now what is left is the left part. We need to determine the U's, and to determine the U's, we need to work on the second matrix, which is AAT. So we need to use these singular values as eigenvalues to find the singular vectors. Yes, Abdullah.
Doctor, why did you divide by 1 over square root of 2?
Yeah, because again, the eigenvectors we generated 1, 1, and 1 minus 1 are not unit length. So the length of this vector is square root of 2. You got it, Abdullah?
Okay. Yes, thank you.
So when we divide by 1 over root of 2, we get a unit vector. So we have a kind of, now we have an orthonormal basis. So as you know, in linear algebra, when you define a vector space, you need we usually use an orthonormal basis. So a set of vectors which could generate the whole space. They are orthogonal and they have unit norms. Why they have unit norms? So you make sure that everything is scaled to 1. Right? So that's why we divide by 1 of the norm of one of the vectors. And if you work your way with the second part, you can determine the U's now. Why? Because you can even obtain it directly without solving the eigenvector equation. So each one of you U's would verify this relation. You see it? Because sigma I, in fact, equals AVI. So basically, you can say that each one of the UI's is equal to AVI over sigma I. So this way, we obtain the first left singular vector U, which is 45 over root of 10 times 1 over 3, tau 1 and 3. And this is the second one. And you can conclude and say that you obtained the two beautiful matrices U and V. So we place it here in the column of U, the two left singular vectors, 1 and U2. In V, similarly, we place the two beautiful right singular vectors, V1 and V2. And in sigma, we place the singular values, as you see. So what happens here? Okay, guys, any question? So let's understand what we were able to accomplish till this point. First of all, this now writes matrix A as U times sigma times VT, which kind of splits into rank 1 matrices. And you can see that two rank 1 matrices we can obtain if you detail here. If you do so, this is A, basically. This is A 3045. Would be written as the first part, which is root of 45 root of 10 times 1 3 1 3. Okay, and the second part, which is root of 5 over root of 20. If you do the multiplication, 3 minus 1 minus 1 1. Got it? So we were able to write this non-symmetric matrix as the sum of two rank 1 matrices. Okay, guys? Okay. So yes, Abdulaziz. Abdulaziz, go ahead.
Doctor, regarding out of this material, is this with us in the quiz?
So we said that the quiz still 1.7. So this is 1.8, Abdulaziz.
Okay.
Okay, don't worry. Okay, so 1.7 means still positive definite matrices and the application minimization. So let's conclude with some observations. So first of all, you could observe that U and V would contain orthonormal basis of the column space and the row space of A. Hello? So, and more than this, the achievement here is that the two bases diagonalize A in a way that A equals U sigma, yes. Okay? So previous U, because here we are not able to write A equals LU. Okay? So, but we still can work our ways to write AV as U sigma. And more important is that every matrix is the sum of rank 1 matrices with orthogonal U's and orthogonal V's. Okay? So this is one of the fundamental parts in when you try to learn from data using data science techniques. Right. If you have any question about the quiz, guys, so the quiz, inshallah, as I said in my announcement, as we discussed before, so the quiz is from 8 to 9 p.m. Okay, on Saturday, and the homework, first homework, it goes from 1.1 till 1.7. Okay, so if you allow me, yes, Khalid.
Doctor, can you delay the quiz to the time of class on Sunday?
No, we don't have this luxury, Khalid.
Doctor, we have another commitment at Saturday.
What do you mean by commitment here?
I have a commitment at Saturday. I cannot make it to the quiz at Saturday night.
Okay, you cannot make it. It's not a problem. But
How
we
can
discussed
that
that, Khalid, we discussed that long ago. We said that our first quiz would be on Saturday, and I sent the announcement before.
We said that we will discuss that at Thursday, Doctor. That's what we said at Sunday.
I'm pretty sure this is recorded, and we said that the quiz was said to be on Saturday night. Anyways, we can work at the next time, but also we have a lot of material to cover, so we don't have the luxury, unfortunately, to offer this quiz on during class time.
Doctor, I sent you an email that I have a PMP course on Saturday.
I think I answered you. Are you Muhammad?
Yes, but I cannot skip the course, Doctor.
Well, you cannot skip it, but you cannot skip the quiz at all.
Yeah, that's why we're asking to change the time of the quiz.
Okay. So what is your suggestion? Which time you prefer?
For me, I think the class time is good.
Okay, I think I cannot offer it in course time. So what is the answer now? What is the solution? Can you think about some solution? Someone has a commitment, someone is taking an extra curriculum course for 4 hours. So I cannot satisfy everyone, guys. I announced it before that we will have, like last time you had to submit a homework and you will kind of free yourself. Now, we
Doctor,
with,
I think,
yes?
Doctor, no problem to make it Saturday after his PMP course, maybe 10 o'clock or Sunday.
So Sultan, I'm pretty sure anyone would come with another commitment. So if this is a fundamental, I cannot satisfy everyone. So this is a commitment to you. I can also remove quizzes if you wish. Okay, so I basically base the grade on attendance or participation. So this is a luxury. We can afford to have the quiz on class time. Period. If you have a commitment, if you want to go out with your friend, if you have extracurricular courses, I do fully understand that. This is your life, you're free to do it. I have mine too, but I don't impose it on you. So I'm taking my time to prepare a quiz to give it to you Saturday night. Whether you want to attend or not, it's up to you.
Doctor,
is clear for everyone. Yes, yeah.
Doctor, you may be able to extend the quiz time on Saturday night.
Yes, well, this is one of the possibilities, but it would be supervised in that case.
Mm-hmm.
Do you get my point? It would be a supervised, proctored quiz. I don't know if everyone agrees on that. So I'm trying to make your life easy, guys. Okay. So if you give me, a break, if you give me, more lenient, you could be more lenient with me. I can be lenient with you. With these kind of, observations, I cannot accommodate everyone. So everyone is sending requests. I don't receive only from Muhammad or Nawaf. I have many other requests. Okay, and this is the best and the most suitable time. It looks to everyone.
We appreciate it, Doctor. Thank you so much.
This is, look, I can skip the quiz. You can skip, you want to skip the quiz, you have a commitment, very important commitment that allows you to skip a quiz. Go ahead. It's up to you. It's not an excuse to me, but you're free. You're free not to take the quiz. It's your decision. Okay? So if you have any other question with regarding the content of the quiz, you're welcome. You can send me an email. Okay? And sometimes you can send me also a message on MS Teams. It's up to you guys. Otherwise, hopefully you understand the content of the material. I shared the material with you. I posted it on the Blackboard. And I also posted the Python file for the complex matrix, Eigenvalues, Eigenvector computation. Okay, thank you very much. Have a wonderful day. Bye.
Thank you, Doctor.
Ah.